Good morning, Lebanon High School. Pardon the interruption for one additional quick morning announcement. In case you missed it last night, our Lady Warrior basketball team swept Fairfield in the final home game of the season. All three teams, freshmen, JV, and varsity, all win with senior Megan Betcher hitting the game-winning shot with 7 seconds remaining to grab the varsity win. Congratulations to all of the seniors on senior night victory, and thanks to all who came out last night in support of our Lady Warriors. Lebanon High School, have a great day.
So 7.3a, we're finding the volume of the solid that lies between planes perpendicular to the x-axis at x equals -3 and x equals 3. The cross sections are perpendicular to the x-axis are squares, and the diagonals of the squares run from one side of x squared plus y squared equals 9 to the other. Kind of lengthy, sorry about that. So obviously we need to graph something. So we've got a y-axis and an x-axis. And then it's talking about x equals -3. The line x equals -3 is straight up and down at -3. So there's the line x equals -3. Then the line x equals 3 is straight up and down at 3. So it's been a while since geometry when you talked about planes. The planes are flat surfaces that go forever in every direction. So they're talking about a plane perpendicular to the x-axis at that line. So perpendicular to the x-axis at that line. So here's the plane at -3. Here's the plane at 3. So somewhere in between those planes is a solid, because they're talking about the volume of the solid that lies between those planes. So that's what the first sentence says. Okay, so then the cross sections are perpendicular to the x-axis. So don't try to picture this 3D solid, but it's somewhere in here. And if you cut it perpendicular to the x-axis, you get a cross section. Okay, so when we cut the watermelon, what shape was the cross section? It was a circle. But this is different. The cross sections are squares, not circles. So this is the change for today. When we cut the watermelon, when we cut the cantaloupe, the cross sections were circular. So now today the cross sections are squares. So like I said, I don't know what this 3D figure looks like, and it doesn't matter. We don't need to picture it. So I went to the store and got some more visual aids. You can get these are generic saltine crackers. So I got all 4 sleeves of these for 89 cents. Isn't that crazy?
Live off saltine crackers.
Yeah, I mean, you could buy the fancy Keebler ones for like $3.89 or $4, but these are 89 cents. 4 sleeves of it. It's amazing.
Which store?
You should do like the saltine cracker challenge.
Yes.
Maybe later. Okay, I gotta get Elena's quiz. Okay, so the cross sections, the change today is the cross sections are squares. So like I said, I don't know what this 3D figure looks like, but I do know that the cross sections of this are squares. Because if I sliced this right here and then looked inside, it would be square. So here's an example of something that has square cross sections. So this 3D solid that is living in here has square cross sections as well. Probably doesn't look like this, but it has the same kind of cross section. Okay, so here's one of the cross sections. All right, so now we've got to, let's see, those cross sections are squares, and the diagonals of the squares run from one side of x squared plus y squared equals 9 to the other. So we better graph this equation here. What kind of, yeah, that's a circle, right? Center is 0, 0, and the radius is 3. So you go 3 this way to a point on the circle, 3 this way to a point on the circle, 3 down to a point on the circle, 3 up. So this may not look very circular, but you get the idea. So there's my circle. So the cross sections are squares. The diagonals of the squares run from one side of x squared plus y squared equals 9. So it's talking about the diagonals of the squares. So that's the blue line there, right? That's the diagonal of this square. So the diagonals of the squares run from one side of the circle to the other. So I just drew the diagonal of the square. So that line is the same as this line. The diagonal of the square is there, here. So I guess there's a triangle coming out of the wall at us, right? And there's a triangle going back into the hallway. You see that? I wish I could embed this cracker inside the board. That's where it's supposed to go, right? Maybe I could just... But I can't do it. I'm not going to do it. All right, so there you go. So everybody got the picture. So then we slice it again, right? And then the square on the other side is slightly larger than the square on this side because it gets a little bigger as you go towards the center. We don't care about that because eventually we're going to go infinitely thin, right? So it doesn't matter that the square on this side is bigger than the square on that side. So now we have a slice. Before we had a slice of watermelon. Now we have a slice that looks like a cracker. Okay, to find the volume of the slice, you use the formula capital B times H. What does the capital B stand for? The area of the base, right? So when it was the watermelon slice, the capital B was pi r squared. But today, it's not pi r squared. It's the area of the square now instead of the area of the circle, right? So the bases are the top of the cracker, the bottom of the cracker, right? So the area of the base is the area of the square. So what's the formula for the area of a square? Side squared, right? So today the volume is going to be s squared times h. It's the same formula as we've been using before. It's just instead of pi r squared for the capital B, it's s squared for the capital B, since the cross sections are squares. All right, so we got to find the volume of this one slice, and that's that. The height is this, right? So what is that? dx. It's going side to side, so it's dx. So the height is dx. And then I'll just leave this as side squared for now. So that's the volume of one of the slices. Then we've got infinitely many of them from -3 to 3. But obviously I need to translate this s into an x, because I can't have mixed variables in my problem. Okay, so now I need to draw this. So here it is. So So this line right here is the diagonal, corresponds to this line right here, the diagonal, corresponds to that line right there, the diagonal. So I'm looking for this, right? That's what I need for my formula. Okay, so, but I have this in my picture. So now looking at this, the diagonal, if this is the point x comma y, so over x up y, right? Then that distance is y. Everybody okay with that? That's y. So that's y as well, because it's symmetric. So this is y, that's y, so the diagonal is 2y. That's critical right there. Does everybody see why the diagonal is 2y? Okay, so then this is a right triangle. So this is a, well, that's a right angle, so this is a right triangle. So then I can use Pythagorean theorem there. The s squared plus the s squared equals the 2y squared. S squared plus s squared equals 2y squared. So then squaring that, it would be 4y squared. S squared plus s squared is 2s squared. So s squared equals 2y squared. So s is the square root of 2y squared. So now I can take that formula for s and plug it in there, right? So integral from -3 to 3 of the square root of 2y squared. Squared.
So are we using the s squared?
Because that's the area of a square. It's one side times the other.
Yeah.
Good. Is everybody doing okay? So that's kind of nice. Then the square root and the square cancel out, right? So I've got the integral from -3 to 3 2y squared dx. But things are still not completely peachy. Why? Because we still have x's mixed with y's. So now we need a formula for the y that we can plug in that has an x in it. But this point here is on the circle. So the y has something to do with the circle equation. So I can subtract the x squared over. So 9 equals x squared. Sorry, y squared equals 9 minus x squared. Subtracting the x squared over. So then I can replace this y squared with 9 minus x squared. So it's the integral from -3 to 3 of 2 times 9 minus x squared dx. Oh, and I forgot my pi, right? No, I didn't forget my pi. You do that sometimes when you're doing this homework. You forget the pi, right? Why don't you need a pi on this one?
It's the area of the square.
Because it's the area of a square, not the area of a circle, right? So the square has nothing to do with pi. So that's why there's no pi. Volume equals area of the base times height, just this, just side squared times h. Everybody okay? So then you would distribute the 2 and take the antiderivative, et cetera, et cetera. It comes out to 72. We're getting pretty good at that at this point. Don't forget to take the antiderivative, though. Sometimes you forget to take the antiderivative. Don't do that. Okay. So now, for example, 2. Just going to change some of these words. Find the volume of the solid that lies between planes perpendicular to x equals 0 and x equals 8. And the cross sections perpendicular to the x-axis are circles. That run from y equals the cube root of x to y equals the negative cube root of x. Okay, so again, we need x-axis, y-axis like normal. X-axis, y-axis, x-axis. Here's x equals 0. Then 1, 2, 3, 4, 5, 6, 7, 8. Here's x equals 8.
Is that from y equals the negative cube root of x to cube root of x?
Yes. So we have a plane here and a plane here, and the solid is in between those somewhere. Then it's talking about y equals the cube root of x. That looks like this. It's also talking about y equals negative cube root of x. Looks like this. So the 3D solid is somewhere in here. So then when I chop it, don't try to picture the 3D figure. It doesn't matter. We can find the volume of it without finding what it looks like. So when I chop it and look at the cross section, what shape is it? Circle this time, right? Back to circles. So I'll chop it all the way across, and so here's one representative cross section. So that's supposed to be the watermelon slice, right? Does it have a hole in it?
No.
No, it doesn't. It's easier than yesterday's stuff where we had holes. Okay, so still, volume is capital B times H, right? But this time, what's the formula for capital B? Pi r squared. So back to that. So the thickness is this way, right? So the height is dx. Gotta have infinitely many of them. Running from 0 to 8. And it's pi r squared. radius goes from here to there. So if you plot that point, you go over x and up y. So the radius is the y value. So I could put y squared there, right? But I don't want x's mixed with y's. So I can use this formula for the y. Is everybody doing okay? Yes?
How do you know not to use the negative?
Well, it's the same distance down to the negative curve. So I actually could have. But I just chose to use that distance. The distance to y equals positive cube root of x.
Oh,
Instead of that distance, the distance to negative cube root of x.
okay.
But it actually doesn't matter. I could have put a negative in there, and then the negative squared would have gone away, so it would have gotten the same answer. Good.
Okay.
Everybody doing okay? So it's pi times the integral from 0 to 8. Another way to write the cube root of x is x to the 1/3. And then in this situation, what do you do with the exponents? Multiply them, right? So 1/3 times 2 is 2/3. So this is pi times the integral from 0 to 8 of x to the 2/3 dx. Then you have to take the antiderivative, so you add 1. 2/3 plus 1 is the same as 2/3 plus 3/3. So 5/3. Then divide by 5/3, aka multiply by 3/5. I should write 3/5. I'm not going to say 3/5. So then plug in 8. 3/5 times 8 to the 5/3 minus 3/5 times 0 to the 5/3. We can do this. The thirds means the cube root. So cube root of 8 is 2. Then you take 2 to the 5th power. So 2 times 2 is 4, times 2 is 8, 16, 32. So 2 to the 5th is 32, so this is 3/5 times 32. 0 to the 5/3 is 0 times 0 is 0. And then that's 32 over 1, right? So 96 pi over 5 is the final answer. Okay, example 3 is really just some geometry help that I know you need. We're going to find the area of an equilateral triangle. With S equaling 4 times the square root of x plus 2. Okay, so what's an equilateral triangle? All sides are equal, right? How big is this angle? 60 degrees. because the three angles of a triangle add up to 180, and an equilateral triangle will have all the same angles as well. So that's 60 degrees. Every side is that. So 4 square root of x plus 2, 4 square root of x plus 2. Base is also 4 square root of x plus 2. I'm not going to label that one though. Okay, so how do you find the area of a triangle? 1/2 times base times height. Nice. So 1/2 times base times height. So I need to draw in the height over here. The height will make a 90-degree angle with the base. So then what is that angle? 30. Now I'm looking at the triangle that's half the big one. So that triangle is a 30, 60, 90 triangle. Okay, so 30, 60, 90 triangles, you haven't talked about those in a while. On a 30, 60, 90. This is called the short leg, right? This is called the long leg. This is the hypotenuse. How does the hypotenuse compare to the short leg? It's twice as big as the short leg. Okay, so that means if this is 4 times the square root of x plus 2, that means this short leg is 2 times the square root of x plus 2. You probably would have guessed that. You probably would have guessed that this height split the bottom in half, right? But that just proved that it does. So that's 2 times square root of x plus 2. All right, now how do you get the long leg compared to the short leg? It's the short leg times the square root of 3. Somebody's showing off his memory back there.
Oh, it's all the time. I wish you could hear it.
I'm sorry, Grace.
No, it's okay.
I specially chose you because I knew you could put up with it. No, actually it was random. All right, so it's a short leg times the square root of 3. So that's that distance, right? So here's my short leg. Then I multiply that by the square root of 3, and that'll give me that dotted line length. So 2 square root of 3 square root of x plus 2. Is everybody okay? This is a mess. Is everybody okay with that mess? Thank you. All right, so now I'm going to go back to my area formula. And area equals 1/2 times the base, which is 4 times the square root of x plus 2. Because that's the whole bottom of the triangle, right? Times the height, which is 2 square roots of 3 times the square root of x plus 2. So now I'm going to multiply all this together. 1/2 times 4 times 2 is 4. Then times square root of 3. And then square root of x plus 2 times the square root of x plus 2, what's that? So there's a formula for the area of this equilateral triangle. Yes?
Wouldn't it be 2 square root of x plus 2?
No, this 2 times that 4 is 8.
Yeah.
Times that half is.
Like instead of 4 square root of x plus 2. Isn't that the hypotenuse?
I see. You're thinking this should be a 2. Is that what you're saying? No, because 2 square root of x plus 2 was just that. And I'm finding the area of this entire triangle, not just the 30, 60, 90 triangle. I'm trying to find the area of the equilateral triangle, whose base is 4 times the square root of x plus 2. Good. Yeah, there's 2 different triangles up here, so it's easy to get them mixed up. Everybody else good? Okay, so why do you think I showed you the area of a triangle? Because there's going to be a homework problem where the cross sections are triangular, right? So today we had an example where the cross sections were squares. Then we had an example where the cross sections were circles. But there could be some 3D solid where you chop it and you look at the cross section and it's triangle, right? So then this formula here would be the area of a triangle times dx or dy. So that's where that area of a triangle will help you out. You'll take that area formula times the dx or the dy to get the volume of the thin triangular thing, half a cracker if you want, and then add them all up, etc. Is everybody doing okay? Okay, the last thing I need to talk about is something called Cavaliers Theorem. And I need to figure out how to spell this, so would somebody look that up for me? It's in 7.3, so turn to 7.3 in your book if you would. Just one person. I wouldn't care about how it was spelled, but this is being videotaped for all time, so I better get the spelling right. So 7.3, Cavaliers. Okay, so it's C-A-V-I, no, C-A-V-A, okay, so this is Cavaliers Theorem. So I've got a stack of coins here. So if you found the volume of this stack of coins, what would the cross sections be? Circles, right? Okay, good. And so if you found the volume, you could just find the volume of each individual coin and add them up, and then that would be the volume of the whole thing. Okay, so let's say that it's not straight up and down. Let's say instead it's like the Leaning Tower of Pisa. So it's kind of slanted like that, but still circular cross-section, still the same height. How would the volume of that compare to the volume of the straight up and down one? They'd be the same, right? That's what Cavaliers' theorem says. If all the cross-sections are equal and the height is the same, then the volume is the same. So if two figures have equal cross sections and equal heights, they have the same volume. Two figures have equal cross section and equal heights, they have the same volume. And you already knew that. You just didn't know it was called Cavaliers' theorem. So just think, today, you could go to Kroger with this and buy this. Craziness. That's a lot of crackers for 89 cents. Stop. Oh, so you would only have to pay 80 cents and